Hey everyone, in this video we're going to go over section 2.8, the derivative as a function. From last time, what we were doing is, given some function of f, we were trying to find the equation of the tangent line to the function f at some point a, f of a. And what we do is to get the slope of the tangent line, we would use the formula m is equal to the limit as h approaches 0 of f of a plus h minus f of a all over h. And that would give us the slope of this tangent line. And then if we wanted to say find the slope over here, I'm going to call it b, just so we don't confuse these 2 points. Well, then, going through b, f of b, we'd have to recalculate this limit. Our new slope, m, would be equal to the limit, as h goes off to 0, of f of b plus h, minus f of b, all over h. And this would give us the slope of the tangent line over here. Now, we did an example at the end of lecture last, at the end of the video for 2.7, where we were going to calculate the slope of the tangent line in a couple places. So, instead of calculating a number, what we did was we calculated a function that all we had to do was plug in a value of x and it would give us the slope of the tangent line. That's what we're going to be doing in this lecture. So, for any differentiable function, the derivative of that function is also a function. I'll say that again. For any differentiable function, I can even write it. For any differentiable function, the derivative is also a function. The derivative, and right there I would have put a f prime. So for any function f, for any differentiable function f, the derivative f prime is also a function. And in fact, f prime, we know f prime of x gives us the slope of the tangent line for any value of x. F prime is the slope of f for any x. So we can view f prime of x as a function of this slope. So the derivative as a function, or this often gets called the limit definition of a function. And let's get it written right. So let's say, given a number x for which the limit f prime of x, which we'll call the limit as h goes off to 0 of f of x plus h minus f of x all over h exists, we call f prime the derivative of f. F prime of x, the derivative of f of x. Once again, this cursive f is the same as that cursive f. I'm pretty bad about jumping back and forth with my f's. Once we get into, I believe, chapter 4, I will curb that very quickly. The derivative of f of x. And then the book goes on to say, we know that the value of f prime at x can be interpreted geometrically as the slope of the tangent line of the slope of the tangent line to f of x at some point x f of x. Cool, same thing I said, just a little bit more formal back here. Instead of calculating the specific slope at a point, now what we're doing is we are going to be calculating a function that we can, I say, use as a tool. We can use this function to get the slope of the tangent line to some function f of x at any point, for any value of x that this function is differentiable at. So let's use that information to do an example. Okay, so for example 1, what we have is we have the graph of some function f, as we'll call it. And what we want to do is we want to sketch f prime from f. So from the graph of f, we want to sketch a graph of the derivative of f. So when we're looking at f, the thing that we care about is its slope. And there are a couple points. There's a couple critical points. This point right here, if you look, the tangent line is flat. It's not decreasing at any point, it's not increasing at any point. Right here at the tip of the bump, the tangent line is flat. Similarly, about right here, the tangent line is flat. Lines are flat by definition. Horizontal is a better way of saying that, I'm sorry. And at about this point, the tangent line is horizontal. Well, the slope of a horizontal line is 0. So that means at this point, and I'll do it in a different color. I hope it shows up as a different color for you guys. Sorry, I inked my fountain pen and I used permanent ink and it just gets over my hands unless I'm careful. So where we have a horizontal tangent line, the graph of the derivative of f is going to cross the x-axis because the slope is 0, so its y-coordinate is going to be 0. At these points, f prime of x is equal to 0. And now what we're doing is we're graphing the slope. So right here, all through this section, all through here, the function is decreasing. And I'm just going to write DEC. The function is decreasing, it's going down. I want to make sure I'm recording my lecture real quick. There we go. So, the function is decreasing. Since the function is going down, the derivative, f prime of x, is going to be negative. Now, from here to here, the function is increasing. Since the function is increasing, the slope of the tangent line is going to be positive. It's going up. So I'm going to write increasing. And what that means is that f prime of x is bigger than 0. Similarly, going from here to here, as x is increasing, y is decreasing. So in between these values of x, we're back to decreasing, which means that f prime of x is less than 0. And from this value of x on to infinity, f is increasing. So f prime of x is bigger than 0. So let me go over that again. This top, and this is kind of like a chart, the top row is an observation about what f is doing. We'll try and do... This is information about f. This is information about f prime. By decreasing, let's get something. Let's clear something up. For what we're doing, we read left to right. Not everyone does, but I do. And I'm teaching you this assuming that you're going to read from left to right. So that means we're going to read this chart left from right. Our values of x increases that way. Y increases that way. So as the value of x increases, we're going from negative numbers to positive numbers, the value of y is going down, it's decreasing. Well, if we were to kind of trace the tangent line with our pen, that slope's going to be negative. So wherever our function is decreasing, that slope is negative. So f prime, which I'll do with this pen, is going to be negative. And we also know that it's going to be, since we are increasing, the function is going from some lower value of y to a positive value of y, we know we're going to be positive through this entire region. But we are going to go back to 0. We're going to decrease, and f prime of x is going to be less than 0 all through this region, and back to being positive. With the information provided, this, which in green, if you can see it, f prime of x, this is as best as we can do. There are technically infinitely many different graphs I could have drawn. You can't get the precise graph of f prime of x from f. We're making observations. There's something that goes on right here and right here that we haven't talked about yet, but that's okay. For now, we are making an observation about what the value of y is doing. If y is decreasing, then the function is negative. Where the graph of f goes from decreasing to increasing, your derivative is going to equal 0. Wherever you have a horizontal tangent line, the graph, and this is worth slowing down to making sure I say correctly, on the graph of f, wherever you have a horizontal tangent line, your derivative equals 0. On the graph of f, wherever you have a horizontal tangent line, your derivative has a root, has a 0. We're going to be very concerned with horizontal tangent lines in Chapter 3. So for now, just know they're really important for what we're doing. I'll say that. Okay, so we have seen algebraically what this means. We've seen graphically what this means. Let's do an example with some algebra. Given the function, I gotta find where I have put it. Given the function f of x being equal to x cubed minus x, we're gonna find a function for f prime of x. Perfect, so we want to find a function for f of x. There's my notes. Yes, right example. Find a formula for f prime of x is the way the book says it, and then we're going to illustrate that formula by graphing f and f prime on the same coordinate system. So for finding a formula for f prime of x, we need to use the limit definition of a derivative. We know that f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. And we know what f of x is, it was given to us. So we can rewrite this limit as the limit as h goes off to 0 of, we can say, x plus h cubed minus x plus h minus x cubed minus x. All of that still divided by h. Okay, now we have to perform the algebra. We've got to use the distributive property. We've got to FOIL. We've got to deal with this cube. We've got to distribute a minus sign. We've got to distribute a couple of minus signs, actually. There and there. So You guys don't have to show your distribution. You guys can use Pascal's triangle, actually, if you would like, to get that x plus h cubed is equal to the limit, as h goes off to 0, of x cubed plus 3x squared h plus 3x h squared plus h cubed minus an x minus an h minus an x cubed plus an x, all over h. Okay, so at this point, like I said, you want to look up to your original function when you have a polynomial. When you have a polynomial, each of these terms, and terms are things that are separated by addition or subtraction, each of these terms you should be able to find down here and eliminate. So we've got an x cubed up here, I've got an x cubed right here, and I've got a negative x cubed right here. I've got a minus x, I've got a minus x, and I got a plus x. Now at this stage, I just like to go through and rewrite what I have. Equals to the limit, as h goes off to 0, of 3x squared h plus 3x h squared plus h cubed minus an h, all divided by an h. Now we want to factor an h out of the numerator. Call this the limit, as h goes to 0, of an h times 3x squared plus 3xh plus h squared minus 1, all divided by an h. We factored an h out of the numerator so we could use it to cancel with the h in the denominator. We'll go through and do that. This is equal to the limit, as h goes off to 0, of 3x squared plus 3xh plus h squared minus 1. Now we can use a direct substitution property. That says as long as plugging in the value at which we are limiting to into this function doesn't violate the domain of that function, then we're free to do so. We've got a polynomial. They behave very nicely. So when we plug h is equal to 0 into there, 3xh tends to 0, and h squared will go to 0. So we're left with a 3x squared minus 1. So what we have is we have f prime of x is equal to 3x squared minus 1. Now, we're going to graph these, but what we can do is we can use this function to give us the slope of this function for any value of x. So instead of having an a here and we'd have to a value in here and we would get a number out here, now we have a function that we can use over and over again. We can feed it a number and it'll give us a value of a slope. We can feed it a new number and it'll give us the value of a slope. So example 2, we're going to graph it. So what we want to do is the first thing we're going to graph is f. F of x is equal to x cubed minus x, which we can factor to be x times x minus 1 times x plus 1. F of x is going to cross the x-axis, and I'm going to scale this by a half, so that's 1, that's 2, that's 1, that's 2, that's negative 1, that's negative 2, that's negative 1, and that's negative 2. We're going to cross at negative 1. We're going to cross at 0. We're going to cross at positive 1. We're an odd function with a positive leading coefficient, so that means we're going to go off towards positive infinity and negative infinity in the positive x and negative x direction respectively. And since we're continuous, we're going to have to go up, down, and up. So that's kind of what f of x looks like. It should be perfectly symmetric. This part should be able to rotate around this part, and in all honesty, that bump should be a little bit, that's about right. But these two bumps should be at have the same vertical displacement. It's a sketch. So now the graph of f prime of x. Well, f prime of x is equal to 3x squared minus 1. It's a parabola, and we'll try and do this again in another color. It'll go through the point 0, -1. Now when x is 1, we're going to have a height of 2. So when x is 1, we're going to have a height of 2, and when x is -1, we're going to have a height of 2 as well. So we look like this. And here is f prime of x. Notice, and this is a sketch, but this dot, this horizontal tangent line, lines up with where about f prime of x equals 0. It's a sketch, it's hand drawn. Similarly, this point should line up more with that point. If I was going to hit my mark, I would have had to scoot that line in some. Wherever our function is increasing, the slope of our tangent line is positive. And now whenever our original function is decreasing, the slope of our tangent line is negative. And whenever our function f is increasing, the slope of our tangent line is positive. Okay. So let's do another example. And we'll use that piece of paper again shortly. This will be example 3. And we will say if f of x is equal to the square root of x, find the derivative of f. There's totally a t in that word. Find the derivative of f. Well, the derivative of f, that's f prime of x, and that is equal to the limit as h goes to 0 of f of x plus h minus f of x all over h. If this were a regular class and you guys were coming to class and watching my lecture in person, I would require you guys memorize that by the test. Most calculus students are going to have this thing memorized. You guys are taking an online class, there's really no way for me to measure what you have memorized. But I'll have you know, that's kind of the standard homework assignment. You guys would be forced to memorize that and use that on the test, which I'm assigning on Friday. This material will be on the test, and if you haven't seen the announcement on Blackboard with kind of a study guide on it, go and look through that announcement. I think its name was Test 1 More Information or something like that. Limit as h goes to 0 of the square root of x plus h minus the square root of x all over h. So, we would get a 0 over 0. We've been taking limits as h goes to 0 of square roots before. So what we're going to have to do is we're going to have to multiply everything top and bottom. There we go. By a square root of x plus h plus the square root of x all over the square root of x plus h plus the square root of x. That'll be equal to a limit as h goes off to 0 of x plus square root of x plus h times the square root of x plus h will give us an x plus h. Square root of x plus h times the square root of x minus the square root of x plus h times the square root of x. Those are going to cancel, and we're going to be left with negative square root of x times the square root of x, which gives us a minus x, all divided by h. And I've seen on a lot of your guys' homework, you guys are dropping the parentheses right here. Square root of x plus h plus the square root of x. You guys need these parentheses. Without these parentheses, what you have is h times the square root of x plus h plus the square root of x just kind of floating around on the end. What these parentheses do is tell the reader that this h is being multiplied by everything here in the denominator. You guys need these parentheses. Okay, So we've got this positive x and we've got a negative x. They're going to cancel each other out. This isn't a, that isn't a polynomial. So what I said about how all of the terms of your original should cancel out does not apply. This is not a polynomial. These are going to cancel. So I'm going to rewrite what we have. Limit as h goes off to 0 of h divided by h times the square root of x plus h plus the square root of x. I put a little tail on the end of my square root symbol. It just helps me know what's inside the square root sign. If you have 3x like this, I don't know if you guys mean the square root of 3 times x or if you mean the square root of 3x. So I'm in the habit of putting a tail at the end of my square root symbol, kind of like a closed parenthesis, kind of like this opens the grouping and that ends the grouping. That's why all my square roots have tails on them. H in numerator cancels with h in denominator. Rewrite what we have. Limit h tends to 0, 1 divided by square root x plus h plus square root x. Direct substitution property. Plugging h equals 0 into this equation doesn't break the domain any. So that's equal to 1 over the square root of x plus the square root of x. And if you've got a square root of x and another one comes along, you'll have 2 square roots of x. So what we have is 1 over 2 square root of x for our formula. So we'll just write that down here. And so if we take a look, the domain of our original is also equal to the domain of our derivative. Okay, that should make sense because this derivative is giving us information about this function. So if this function isn't defined in a location, how much meaningful information do you think this function could provide us? Okay, let's do another example. This will be example 4. Oh, we'll say we want to find f prime given f of x is equal to 1 minus x over 2 plus x. So f prime, limit definition, f prime of x is equal to the limit as h goes off to 0 of f of x plus h minus f of x all over h. Applying what the problem gave us equals limit h goes to 0 of 1 minus x plus h divided by 2 plus x plus h. I didn't put parentheses because we don't have to distribute anything here. It probably wouldn't hurt just for grouping. So we did 1 minus x plus h over 2 plus x plus h minus f of x, which is 1 minus x over 2 plus x, all divided by h. Cool. So now what we need to do is we're going to have to put everything in this numerator on a common denominator, and then we're going to try and mess with it algebraically. Okay, so let's go ahead and do that. I'm going to do kind of a couple steps at once here. Limit as h goes off to 0. In the denominator of our numerator, we're going to have 2 plus x plus h times 2 plus x. So this term, this term is a 1 minus x plus h times 2 plus x minus 1 minus x times 2 plus x plus h. And this numerator being divided by h is the same as this numerator being multiplied by 1 over h. Okay, let me now distribute these minus signs in the numerator. Limit h goes off to 0 of 1 minus x minus h times 2 plus x minus 1 minus x times 2 plus x plus h all over h times 2 plus x plus h times 2 plus x. Now we need to use our distributive property. This is going to be equal to the limit. H goes off to 0 of, that gives us 2 plus x minus 2x minus x squared minus 2h minus xh. And then from that we're going to subtract, and I'll put these in parentheses. We'll do 2 plus x plus h minus 2x minus x squared minus xh. All of this is going to be divided by h times 2 plus x plus h times 2 plus x. Now we'll distribute our minus sign through. 2 plus x minus 2x minus x squared minus 2h minus xh minus 2 minus x minus h plus 2x plus x squared plus xh all over h times 2 plus x plus h times 2 plus x. Isn't all this algebra beautiful? Now we want to go through and we want to cancel as many things as we can in the numerator. I've got a positive 2. I've got a negative 2. I got a positive x and a negative x. I've got a negative 2x. I got a positive 2x. Oh, I've got a negative x squared and a positive x squared. And I've got a negative xh and a positive xh. The only thing that's left over is this negative 2h, and I'm going to use that h to cancel out with that h, but I'm just going to rewrite down here. Limit h goes off to 0, negative 2h divided by h, 2 plus x plus h, 2 plus x. Like I said, h on top, h on bottom, meet for a dual, and this is going to be equal to the limit. H goes off to 0 of negative 2 divided by 2 plus x plus h times 2 plus x. Awesome. So, let's go through. And then let's finish this up. As we plug h equals 0 into this limit, well, it won't violate the domain of this function, so we are free to do that. That'll give us negative 2 in the top, and we have a 2 plus x times a 2 plus x to give us a 2 plus x quantity squared. I have found my mistake. There's definitely a mistake floating around in there, but believe it or not, it happened when I did addition. Negative 2h minus h gives us a negative 3h, and then that h is going to cancel out with that h to give us a negative 3, and then when we plug h equals 0 into this function, we get negative 3. Negative 3 over 2 plus x quantity squared. Got going a little fast. That's why I honestly do a lot of steps when I go through and do these limits. It always gives you a good point to go back and check. And also, that's why I always do this rewrite step in between my big cancel step and my, between my big cancel step and eliminating the h in the denominator. I always rewrite. It's really easy to miss things, especially when you did a lot of canceling like in this problem. But the process, we find f prime given f, we use that limit definition, we fill in with the function. At this stage, we're going from here to here. First we put the numerator on a common denominator. I didn't show the step, but we did 2 plus x plus h divided by 2 plus x plus h. And over here we did 2 plus x on top of 2 plus x. And then we multiplied everything out. We needed some parentheses over here. And then dividing by h is the same as multiplying by 1 over h. So written algebraically, that's like me saying the quantity of a over b, all divided by h, is equal to a over bh. And that's what we did to go from getting the h here, getting the h here. Magically, somehow, I did all of this multiplication correctly, including the distributing of the minus sign, and then going from this step to this step, I added poorly. But we use the h in the numerator to cancel out with the h in the denominator. That's kind of our standard approach for all of these. You're hopefully at this stage, you're going to have an h in your numerator to cancel out with the h in your denominator. If you don't, go back to all the algebra that you did and see if you can find one. And we were able to calculate that the derivative, f prime of x, is equal to negative 3 divided by the quantity of 2 plus x quantity squared. Cool, so now let's talk about some other notation. So if we have y being equal to a function of x, all the following, everything I'm about to write is equivalent. And I'm just trying to look at my list real quick. So f prime of x. The derivative of the function f is equal to the derivative of the function y. And then we've got some more notation. The derivative with regards to y, or the derivative of the function y with respect to x. You can also say the derivative of f with regards to x. We can also use a capital D, d of f of x, or, and you'll see this one in Calculus 3, d sub x of f of x. So, the derivative of f, the derivative of y, because y is the same as f. This notation, this is kind of when we have d derivative, name of function, d variable. So, because we have been, say, taking the derivative of f with regards to x. The previous example, there would be nothing wrong if we said g of y was equal to 1 minus y over 2 plus y. We know that g prime of y would have been equal to negative 3 over 2 plus y squared. Same thing that we did over here. I just changed f to g, and I changed x's to y's. And probably y isn't the best one over here, so I'm going to go through for the sake of argument and make these z's. just so, because we got y's floating around up here, I don't want any y's floating around over here. Cool. So all of this notation applies to y is equal to f of x. But down here, we're going to have y is equal to g of z. And so we would have g prime of z being equal to y prime being equal to the derivative of y with regards to z. Or we could talk about the derivative of g with regards to z, or the derivative of g of z, or the derivative with regards to z of g of z. So hopefully you guys see the parts of these that change. Like we can put, we'll put something different here. We put something different here. The variable that we can take a derivative with regards to can change. We just typically call them x. But everything we've discussed so far holds true. If we just call x a different name, like z, and then, once again, the name of the function. The name of the function and the variable we're taking the derivative with regards to. The name of the function and the variable we're taking the derivative with regards to. These are the standard way of issuing. These are the standard way of writing things. Typically, we have y as a function of x, and everything will look like this. But there's nothing sacred about that. Y can be a function of z, in which case we could rewrite everything like this. There is another one I skipped over, and that is dx of f of x. And then similarly with this analogy down here, we would have dz of g of z. So this dx, and I'm going to talk exclusively up here. This ddx, let's do a different color once again. I know this one renders a different color. This ddx, this capital D, and to a lesser extent that capital D because it has a subscript. ddx and capital D and I'm not going to write in an expo on paper. These are called differential operators. And they denote the operation of differentiation. So kind of like how we say the plus symbol denotes the operation of addition, or the minus symbol with subtraction. ddx, or D, denotes differentiation. So going back to some of the previous examples, if we had, we could say that the dx of x cubed minus x was equal to 3x squared minus 1 from the work that we've already done. If we knew that f of x was equal to, and I want to make sure I copy it right, 1 minus x over 2 plus x, 2 plus x, we could say that the derivative of f of x is equal to, that was negative 3 over 2 plus x squared, if I remember correctly. So this is telling us to do things. Instead of saying find totally doesn't have an E at the end of it. Find f prime of x. Instead of saying find f prime of x, you could just say calculate this. You just say calculate. So, equivalent notation. Being told to find f prime of x is the same as being told to find y prime, provided that y is a function of x. What's really common is seeing the d dx of f of x. d dx of f of x is one of the way more common ways of seeing derivatives written. F prime is another super common way of seeing things written. Let's see. Y prime gets used a lot in differential equations. F prime and d dx, that gets used kind of across all of mathematics. df dx. Once again, I've seen that notation used more in diffeq. And people who study differential equations might argue this with me, but for what you guys are going to be doing, differential equations is effectively a applications to a calculus class, I'll say. There's a lot more you can do with it, and what I just said might be fighting words in some circles, but differential equations is largely an application of calculus. And then the d of f of x, this is a little bit overkill. What gets more used is d sub x of f of x. We'll start seeing that when we have functions. We'll say z is equal to x squared plus y squared plus x minus 2y plus 1. And we can calculate the change of this function with regard specifically to one of these variables. So this notation, Calc 3. This notation, I told it to you guys because the book suggested I tell it to you guys. These two bits of notation really get used in differential equations. This I'm going to use a lot here in calculus, but they all mean the same thing. Newton and Leibniz went back and forth in the mid-1600s trying to develop calculus. And what we have is over here is Leibniz. And let me make sure I spell his name correctly. Starts with an L, I know that. I'm trying to find the spot in my notes. L-E-I-B-N-I-Z. L-E-I-B-N-I-Z. Leibniz notation. And over here is Newton. Sir Isaac Newton. Newton and Leibniz developed calculus at the same time for different reasons. So the notation that they use is different, but it lends itself to what they were doing. And also for now, don't view ddx and don't view dy dx as a fraction. View them as a whole thing. We're going to break them apart and use them like a fraction later, but for now, the ddx and the dy dx, that's a whole entity. So yeah, Newton, Leibniz developed notation to do different things. Later, they realized the things they were doing were equivalent, and the notation was the same. So that's why we have this kind of two schools of thought about the way calculus should be written. Really, math is kind of a creative endeavor. There's no right way or wrong way to write something in math as long as you are effectively conveying your idea. So I don't care if you use Newton or Leibniz. I pretty much exclusively use Newton, unless I used this a lot more in grad school for what I was doing, or in Calc 3. Fun fact though, calculus as a whole is newer than Harvard. Harvard came about in, I think, 1633, according to the wiki. And Newton, I believe, said that a bulk of his research in calculus came in like the 1660s, so 30 years after Harvard became a university. I always thought that was kind of a fun fact, that Harvard is older than calculus. Some more notation. Those are differential operators. That's Leibniz for now, not viewed as a ratio. Also, so this one might get you. the derivative of f at a certain point with Newtonian notation is the same as saying the derivative of y with regards to x evaluated at x equals a. And this is for some function of x that we call y. So we have the derivative of f evaluated at a is equal to the derivative of this function evaluated at a. You might also see f prime of a being equal to the derivative of y with regards to x, and they'll put a bracket. X is equal to a. Math is old, symbols kind of change. These mean the same thing, but this is read the derivative evaluated at a is equal to the derivative evaluated at a, or the derivative evaluated at a is equal to the derivative evaluated at a. So let's give you a definition on as a part of this, and then we'll shift gears. So definition, and this is for differentiable at a. Differentiable at a. So a function f is differentiable at a if a prime exists. Not a prime, f prime of a exists. If it is differentiable on the open interval, okay. And then f is differentiable on an open, O-P-E-N, interval. And by open interval, that could be anything like a to b, a to infinity, negative infinity to b, or negative infinity to infinity. Any open interval. F is differentiable on an open interval if f is differentiable at every point in that open interval. So f is differentiable if that limit exists. And remember, f prime of a is equal to the limit as h equals 0 of f of a plus h minus f of a all over h. In order for this limit to exist, the limit as h approaches 0 from the left of f of x, we'll say f of a I should say, is equal to the limit as h approaches 0 from the right of f of a. So, f of a is a number, so that's, I would go back to an x. Either way, we need this limit to agree as we approach from the left and approach from the right. So we will do an example and show you what I mean by this. Cool, so let's explore that definition with an example. This will be example 5. And example 5 is asking, where is the function f of x being equal to the absolute value of x differentiable? Yeah, differentiable. So the absolute value of x, we're going to do this in some cases. So our first case is we're going to explore, so in order for, I'll back up, wherever it is differentiable, a number f is differentiable at a if f prime exists, okay? So let's check what happens for all values of x that are positive. Okay, well, for all values of x, f prime of x is going to be equal to the limit as h goes off to 0 of the absolute value of x plus h minus the absolute value of x all over h. I jumped straight into the limit definition. Now, for all values of x that's positive, h is going to go to 0. So whatever value we wind up adding to x, this thing is going to be positive. X is positive, and h is going to eventually go to 0. So at some point, even if h is coming at it from a negative direction, it's going to be closer to 0 than x is. So for what we're doing, when x is positive, this is equal to the limit as h goes off to 0. If x plus h is always going to be positive when h gets sufficiently small, we can replace this with x plus h. Now minus the absolute value of x. If x is always positive, then the absolute value of x is always equal to x, and we get minus x. All this is going to be divided by h. Our x's are going to cancel, and we're left with the limit as h goes off to 0 of h divided by h, which is equal to the limit as h goes off to 0 of 1, which equals 1. And we'll do this split screen left and right. For values of x that are less than 0, well, f prime of x is still going to be this. Limit h goes to 0, absolute value of x plus h, minus absolute value of x, all over h. Now, if x is a negative number, and h eventually goes to 0, that means x plus h is eventually going to be a negative number. So that means we can replace this with the limit as h goes off to 0. If x plus h is a negative number, then the absolute value of x plus h is equal to a negative x plus h. And then we're going to minus, and once again, if x is negative, the absolute value of x is equal to a negative x all over an h. We got a couple minus signs to distribute, so we will do so. And we'll rewrite. Limit h goes off to 0, negative x, negative h, positive x, divide by an h, cancel, cancel. Limit h goes to 0 of a negative h over an h. Well, that's the limit as h goes to 0 of a negative 1, which is equal to the limit, which is just equal to negative 1. Well, that's what. So when x is bigger than 0, regardless of what the value of x is, our derivative is equal to positive 1. And regardless of what the value of x is, as long as it's a negative number, its derivative is always going to be equal to a negative 1. Well, let's check what happens when x is equal to 0. Well, going back up to this definition, f prime of x is going to be equal to, well, f prime of, 0, I could say. F prime of 0 is going to be equal to the limit as h goes off to 0 of the absolute value of h minus the absolute value of 0, all divided by h. So the derivative at 0 is equal to this. Well, the absolute value of h, and maybe I should have written this in the beginning, the absolute value of any function is going to be equal to h if h is non-negative, or negative h if h is negative. So that means when we take the limit as h approaches 0 from the left, as we're approaching 0 from the left, h is always going to be negative. So that means we can rewrite this limit as going to be negative h all divided by h, which is going to equal negative 1. And now the limit, as h approaches 0 from the right, well, h is always going to be positive. If h is positive, the absolute value of h is equal to h, and we get h divided by h, which is equal to a positive 1. So look, this limit existed for any value of x positive than 0. If we went to h from the left or h from the right, we would always get 1. When x was less than 0, our derivative was always equal to negative 1. So we know that the derivative exists, or that this function is differentiable on the open interval from 0 to infinity. And we also know this function is differentiable on the open interval negative infinity off to 0. But what we have shown right here, when x is equal to 0, the limit of our function as h approached 0 from the left was not equal to the limit of our function as h approached 0 from the right. So we know by that previous definition that the function f of x is equal to the absolute value of x is not differentiable. Well, we'll write this in a different color. The absolute value of x is not differentiable at x equals 0. It's differentiable anywhere else. We can take the derivative on 0 to infinity or negative infinity to 0, but at this point, x is equal to 0, we are not differentiable. So let's graph that, and that'll lead into a discussion. Let me find where I put down my graph paper. And we can use this one. So example 5. So I'm just going to graph the absolute value of x. The absolute value of x goes like this and like this. Okay. Sorry, my cat's screaming at me. So notice how we have this sharp point here. And if you notice, we've got this slope of positive 1. And we have this slope of negative 1 on this side. But derivatives are like being able to balance your pen on the graph of the function. And you're asking yourself, well, what's that slope? The absolute value of x has a sharp point on it. So there's not one way you can really balance your pen. Not all functions are going to be differentiable everywhere. What do you have to watch out for? You have to worry about corner points. If you have something sharp, then your function is not differentiable at a. You can't take the derivative here. If you have a discontinuity, because the limit of this slope might not be equal to that slope, then you don't have, then you're going to have, and these should have arrows on the end for good measure. They don't really need them. They could be segments, where they can have a restricted domain. But wherever you have a discontinuity, like right here, you're also not differentiable at a. And over here, one that we haven't talked about, is if you have a vertical tangent line, and we'll discuss vertical tangent lines more. If you have a vertical tangent line, your function is not differentiable at the point A. So, the three big things that we're looking for is we're looking for sharp corners, like on the absolute value of x. We're looking for discontinuities, like with kind of piecewise defined functions, or where these things naturally arise, or wherever we have a vertical tangent line. You know that your function is not differentiable at these 3 points. And honestly, I have transitioned from being more algebraic in my approach to mathematics to more geometric in my approach to mathematics. This is the way I determine if a function is differentiable. There's only 3 conditions you have to check: sharp points, jumps, and vertical tangent lines. So if you ever see any of those 3, your function is not differentiable at A. And notice how all of these happen at A. So, not differentiable there. Let me look over my notes one time and make sure I told you everything I wanted to tell you. One more thing to add to that, a theorem, probably the most important thing to add to that. So our theorem says, if f is differentiable at A, if f is differentiable at A, then f is continuous at A. Worry about covering up our zebra. I autofocus on at least the camera I use works off by detecting contrast. So I printed off a generic high contrast image, and I'm worried if I cover it, we're going to have issues with autofocusing. It's been a process learning about how to take videos. So if f is differentiable at A, f is continuous at A. And in all honesty, continuity is a little bit easier of a question to answer than differentiability. There's a thing in set theory, formal logic, that says if A implies B, then the opposite of B implies the opposite of A. This isn't the formal notation for it, but that's the idea. If A implies B, then not B implies not A. This is called the contrapositive. It's kind of like, if I drive, I buy gas. If I don't buy gas, then I don't drive. So, if f is differentiable at A, then f is continuous at A. The contrapositive says, if f is not continuous at A, then f is not differentiable at A. So this is our theorem. This is our contrapositive to the theorem. We derived this logically from this, so these two have equivalent results, and this one's a lot easier to work with, so let's work with the easy one. If f is not continuous, well, right here, we can see that f is not going to be continuous. If f is not continuous at A, then then we automatically know it's not going to be differentiable at A. Say that again. If f is not continuous at a point, then f is not differentiable at that point. So that kind of gives rise to the reason why we're not differentiable at this point A. So let's move on. While we're at it, we'll keep it rolling. I've also been experimenting with with how I set up the camera, for lack of better terms. So, higher derivatives. Okay, so we can take the derivative of a derivative. So if we have some function y that equals f of x, our first derivative is f prime of x. Or you can think of it as the derivative with regards to x of f of x. Or you can think of it as the derivative of y with regards to x. And I'm doing all three on purpose. We can, if we take the derivative, because remember the derivative of a function is a function itself. If we can take the derivative of this function, well, our second derivative, and that's what we call it. We have a first derivative, we have a second derivative, the next one's going to be called a third derivative. Our second derivative is f with two tick marks, x, or this is the same as saying the derivative with regards to x of the derivative with regards to x of f of x. Or, and watch this one over here, this is saying we took the second derivative of y with regards to x. The second derivative of y with regards to x. The two jumps from what it's attached to. This notation, like I said, you'll see stuff like this in differential equations. This always messes me up. Even when I was in grad school in a room with just a bunch of grad students and professors, we all always forget, do we put the 2 on the y or do we put the 2 on the x? This will take some time to get used to. We're here because we're learning. Our third derivative, it follows the pattern. F triple prime of x is the derivative with regards to x of the derivative with regards to x of the derivative with regards to x of f of x, close bracket, and now we would take the third derivative of y with respect to x. This pattern can continue. I'll show you the fourth and then we'll do it in the general case because the first, second, and third follow this pattern. The fourth instead of doing these tick marks, it's common, just put a 4 in parentheses as a superscript. This is getting long and drawn out, so I'm going to skip it. We'd put another ddx right there. Over here, we would say the fourth derivative of y with respect to x. And if we put the 5, we'd put a 5 there and a 5 there and there. If we wanted the 6, we'd put a 6 there and a 6 there and there. So that means if we wanted the nth derivative, well, that would be f with a little n in parentheses. It's not an exponent of x. Once again, now there would just be n of these ddx's floating around in here before an f of x. dn of y over dx to the n. Over here you use parentheses around the numbers just so you don't confuse it with an exponent. This is kind of a standalone thing that only looks like itself, so you don't need to put parentheses around here. I don't want to call them exponents, but they are effectively in the position of an exponent. But yeah, we can take the derivative of a function. We can take the derivative again and again and again. Some functions you can take the derivative an infinite number of times if you like. This notation, this one in this column, is going to be used most common. This notation over here, I would say, is going to be second most common. And this is useful. This is more of a command. This is telling you to do that. This is telling you to do that. This is telling you to do that. This is very much an operation. This can be viewed as an operation, or this can be viewed as a name of a function. These are pretty exclusively names of functions. So let's go through. And I got a backup page. So this is that same function over and over again. We've got f of x being equal to x cubed minus x. We have had the joy of discovering what f prime of x is, and that was 3x squared minus 1. Now, it's the gift that keeps on giving, we will find the second derivative of x. Well, that's going to be equal to the limit, as h goes to 0, of f prime of x plus h minus f prime of x all over h. Sorry, that cat has knocked over my camera from time to time. She commands attention whether I want to give it to her or not. Limit, h goes off to 0. Well, f prime, we'd get 3x plus h squared minus 1 minus 3x squared minus 1 all over h. Yes. There you go. So, now we get the limit as h goes off to 0 of 3, and I'm just going to call this x squared plus 2xh plus h squared minus 1 minus 3x squared plus 1 all over h. Nope. We'll distribute that 3. Limit as h goes off to 0 of 3x squared plus 6xh plus 3h squared minus 1 minus 3x squared plus 1 all divided by an h. Solid. So we're taking the derivative of a polynomial. Like I said, with polynomials, all of your terms in your polynomial. Sorry about that. Once again, my battery died. So, like I was saying, I want to double check that I'm actually recording. Very good. So, we got a polynomial. We're taking the derivative of a polynomial. All of our terms in the polynomial should be canceled out down here. Should be canceled out in the numerator, I think I was going to say. So we've got a 3x squared. If you look down here, we've got a 3x squared. They'll cancel with that negative 3x squared. We've got a negative 1. We've got a negative 1 and a positive 1. At this point, I just rewrite everything. Equals the limit. H goes to 0. 6xh plus 3h squared all over h. This h is going to cancel out with one of those h's and one of those h's. Turn this into the limit as h goes off to 0 of 6x plus h, 3h, sorry. And as h goes to 0, this equals 6x. So, we've shown that f double prime of x is equal to 6x. Sorry, I'm trying to find where I left my stack of papers. There's a piece of paper. Good enough. Pardon the crinkles. So that's f double prime. Let's calculate f triple prime. Well, that's going to be equal to the limit as h approaches 0 of f double prime of x plus h minus f double prime of x all over h, which is equal to the limit as h goes to 0. F double prime is 6x plus h minus 6x all over h. We'll distribute equals limit. H goes to 0. 6x plus 6h minus 6x all over h. Once again, we're taking the derivative of a polynomial, so all of the terms of our polynomial should cancel out in our derivative. 6x and a negative 6x. Those will cancel. Those will cancel. Well, and we've got an h down here and an h up there, so those will cancel. So this whole thing reduces to the limit as h approaches 0 of 6, which is just equal to 6. And finally, we'll calculate the fourth derivative of f of x, which is equal to the limit as h approaches 0 of f triple prime of x plus h minus f triple prime of x all divided by h, which now would give us the limit as h approaches 0 of f triple prime of x, and we have this right here, f triple prime of x is equal to 6. So f triple prime of x plus h is equal to 6, and f triple prime of x is just equal to 6, all divided by h. Once again, we're taking the derivative of a polynomial, so every term in our polynomial should cancel. 6 take away 6 is 0. The limit as h approaches 0 of 0 divided by h is 0. Anything with 0 in a numerator is going to be is going to equal to 0. And in fact, this is something like 0 over 0.1, 0 over 0.010 over 0.001. All these are equal to 0, so as the denominator gets really small, either in the positive or the negative direction for what we're doing, this whole thing limits to 0. So, let me mad scramble, hopefully, for our, we've got a good piece of paper there, and then this graph. So earlier, this is the graph of f of x, that x cubed minus x we've been dealing with all lecture. And then we've got this f prime of x being equal to 3x squared minus 1. We calculated f double prime of x to be equal to 6x. Oh, and at 6x, when we are out here at 1/2, we want to be way up here at 3. And that's off of our chart, so it would be something like this. 1, 2, 3. And when x is negative 1/2, we're down here at negative 3. And then f triple prime, and I'll switch these up in colors. F triple prime of x was just the line y is equal to 6, which would be somewhere way up there. Remember, this is scaled by, each of these tick marks is a half, so if that's 2, that's 4, and 6, so it would honestly be way up here on this chart. And the fourth of x was equal to 0. So analyzing what all of that means. So we've got a function, we've got its rate of change, we've got the rate of change of the rate of change, the rate of the change of the rate of the change of the rate of the change, and the pattern continues for up to the fourth. In our original, wherever our function was increasing, our derivative was positive, and wherever our function was decreasing, our derivative was negative. Now, if you look at f prime, wherever our function was decreasing, the derivative was negative, and wherever the function was increasing was positive. Now, if you look at the derivative of this line, this function is always increasing, so that's why this function is always positive. And finally, the derivative of a constant, well, it's never changing. A constant function is almost a horizontal tangent line by itself. So you are never changing. The value of y never changes as x increases or decreases. That's why the derivative of a constant number is always going to be 0. Once we get into chapter 3, we're going to go through, we had limit laws, we're going to have derivative laws, and we're going to get away from the limit definition of taking a derivative. And you guys will be able to quickly jump from there to there, back over to there. But for now, what we're doing is we're using the limit definition of a derivative to find the derivative of a function and write it as a function. So that was example 7. So just kind of a discussion at this point. So you can pause it and read if you want to. This is pretty shamelessly stolen from the book. So you guys have already experienced this derivative of a derivative. If we called s some position function, well, the rate at which you change your position is equal to your velocity. And the rate at which you change your velocity is equal to your acceleration. If you guys go on and wind up taking a a calculus-based physics class, this is how you guys are going to convert from your position to your velocity to your acceleration. And by the end of this, not chapter, not unit, what do we call them? Semester. By the end of the semester, by the end of Calc 1, you'll actually be able to go the other direction too. Right now we're using derivatives only to go one direction. We'll use an antiderivative to go the other way. So position, your change in position is your velocity. You're changing your velocity as your acceleration. They go on to say that your change in velocity, your change in acceleration is called your jerk, because if you have a rapid change in acceleration, that feels like a jerk. doesn't really get used in my experience that often, but I'm a mathematician, so I don't know necessarily all the lessons you guys take if you go on to be a physicist or an engineer. The big three are position, velocity, and acceleration. Your change in acceleration gets called your jerk. For what we're doing though, I'm going to ask you guys to do second derivatives, third derivatives, fourth derivatives. You guys are going to just do all sorts of derivatives, especially in chapter 3. For homework, go off and do the thing I have there. 1, 3, 21 through 31 odd, and 55. This is going to be due this Friday. Your test is going to go live this Friday, and your test will be due on Sunday. Everything up until that point is free game on your test. I put a study guide, kind of a study guide up on Blackboard. Go ahead and look that over and let me know if you guys have any questions. One thing, and the stars just weren't aligned for me on Monday. A lot of times we've been or what we were doing in 2.7 is we're going to be given some curve, like y is equal to, and I don't know, we can do, what's something that'll behave nicely? I don't know, we'll do 3x squared plus x minus 1. And what we want to do is we want to find the slope of the tangent line. And that's an L, not a T, and they'll give us a point. Like if we call this thing f of x, f of 1 is equal to 3 plus 1 minus 1, which equals 3. So we're going to find the slope of the tangent line to this curve at the point 1, 3. So what we were doing last time is we were using this formula, y minus f of a is equal to f prime of a times x minus a. Where in this problem, we have an a and an f of a. We've got f of a to be 3, and we've got x, and we've got a to be 1. So what you guys would have been doing is you would calculate f prime of a is going to be 3, which is going to be equal to the limit, as h goes off to 0, of f of a plus h minus f of a all over h. Same thing as what we did all lecture long, except for we're finding the slope once at a specific point. Equals the limit as, that would be 3 times, we'll say, actually, f of 3 plus h minus f of 3. A is 1. A is 1. Limit h goes to 0, f of 1 plus h minus f of 1 all over h. So that would give us the limit as h goes off to 0. F of 1 plus h is going to be 3, 1 plus h, plus 1 plus h, minus 1, minus f of a, we already know that f of a is going to be 3, all over h. And this is squared. Sorry about that. So we've got 3a plus h squared plus a plus h minus 1, all minus f of a, which is 3 all over h. If we use the distributive property, that'll give us 3, 1 plus 2h plus h squared, plus 1 plus h minus 1 minus 3, all over h, which is equal to the limit, as h goes off to 0, of 3 plus 6h plus 3h squared, plus 1 plus h minus 1 minus 3, all over h. And this plus 3, going to cancel out with that minus 3. And that plus 1, going to cancel out with that minus 1. And that h is going to cancel out with one of those, is going to cancel out with that h, and is going to turn that h into a 1. So we get the limit, as h goes off to 0, of 6 plus 3h plus 1 plus 3h plus 1, yep. And as h goes to 0, that's going to be equal to 7. Which makes sense, yes, because that would be 7, which equals 7. So what we have found the slope for this equation. And before working frantically, he searches for a piece of paper that contains no writing on the back half. There we go. So, last step is to fill in this equation. Y minus f of a is 3 is equal to f prime of a, which is 7, times x minus a, which is 1. Well, I guess the last step is now to use algebra. Y minus 3 is equal to 7x minus 7. Y is equal to 7x minus 4. Is the equation of the line that is tangent to this curve at this point. With what we did today, you could go through and you could calculate f prime of x and then plug x equals 1 into the derivative. I just wanted to give you one straight through example. Again, here's a curve. I came up with a point. That's what this is. I kind of came up with this example on the fly. I figured you guys might want to see another one. So we know this point 1, 3 is on this curve. We wanted to find the slope. Well, we wanted to find the slope of the tangent line. We went all the way through and found the equation of the tangent line. Equation for the tangent line we can use this equation for. We calculated f prime of a. In this case, a was equal to 1. I put 3 right here. And I really should have put a 1. But I canceled that out, so we'll write this right here. F prime of 1 is equal to this. And we found the slope to be 7. And then once we found the slope, we plugged it into point slope form to get the equation of the tangent line. You guys are going to be expected to do this on the test for a variety of different curves, at least once. I, in all honesty, haven't written the test in its entirety yet, so I can't tell you what's going to be on it. I was able to tell you what's not going to be on it, though. So like I said, go over that study guide, go over the homework I just assigned, and let me know if you have any questions. Send me an email, you guys. I'll talk to you later. Bye-bye.